In this video, we are going to discuss about measurement of power in three-phase systems. When we had a power in Ohm's law, power in Ohm's law is found by P is equals to V squared over R, or P is equals to I squared R. But in this case, we're going to look into three-phase systems where we have balanced or unbalanced loads. So to start with, we have different types of methods that are used to measure power in three-phase loads. The first one is the one-wattmeter method. The one-wattmeter method for a balanced load. In this case, it's for a balanced load. So wattmeter connections for both star and delta are shown in our next figure. The power connections, we have this one. The power connection of a one-wattmeter method, we have the first, this is the current coil here, this point, at this point, we have a current coil, then we have a voltage coil, then we have our M, then we have V plus, then we have an L. So a one-wattmeter, this is a one-wattmeter for either star or a delta connection. We have a star connection, or sometimes known as a T, or a delta connection. So this is for a balanced load for either a star or a delta connection. So to find the total power in using the one-wattmeter method for a balanced load, the total power is given by 3 by the product of the wattmeter reading. For example, if you had a wattmeter reading of 50, you had a wattmeter reading of 50 watts. So the total power will be 3 multiplied by 50, which will give you 150 watts. So 3 by 50, which will give you 150 watts. That is how you calculate power, the total power in a one-wattmeter method. Moving on to our next method. Our next method is a two-wattmeter method for balanced or unbalanced loads. Two-wattmeter method for balanced or unbalanced loads. A connection for this method is shown below. This is the connection of the two-wattmeter method. That is the connection of a two-wattmeter method. The similar connections are made for a delta load. This is a star. This is star connected. This is star connected. This is a star connection of a two-wattmeter method. So here we have wattmeter 1, and then we have wattmeter 2. So that shows how, this is how the connection is done for either balanced or unbalanced loads. To find the total power of the two-wattmeter method, you sum the wattmeter readings. For example, if you had power 1, or in wattmeter 1, that is P1 of wattmeter 1, for example, you had 40 watts, and in power 2, you had 100 watts. So when you find the total power in the two-wattmeter method, you add P1 plus P2, to get the total power. Total power is equals to P1 plus P2. So we had our P1 as 40, so 40 plus 100, which will be equal to 140 watts. That will be the total power in two-wattmeter method. Moving on to our next method. So the total power may be determined from using a tan phi. You can also use a tan phi. Tan phi will be equal to the square root of 3 into brackets P1 minus P2 divided by P1 plus P2. So you should note that it's possible, based on the power factor of the load, for one wattmeter to be reversed to obtain a reading. In this case, it's taken as a negative reading. That one will be taken as a negative reading. So the power factor, so this is how you determine the power factor. This is how you determine the power factor of a 2-wattmeter method in balanced or unbalanced loads. So this is how to find the power factor. That is how to find the power factor. Moving on to our next method, the third method and the last one, we have a 3-wattmeter method. A 3-wattmeter method. We have a 3-wattmeter method. 3-wattmeter method. We have the first one was 1-wattmeter. The second one was the 2-wattmeter, and now the third one is the 3-wattmeter method for a 3-phase, 4-wire, balanced or unbalanced load. 3-wattmeter method for a 3-phase, 4-wire, for balanced and unbalanced loads. So we can see from our figure here, figure 3.13. From our figure 3.13, we have wattmeter 1, we have wattmeter 2, and wattmeter 3. Of course, we have our voltage coils, our current coils in the 3 wattmeters. So, and this is a star connection. A similar connection is made to the delta connection. A similar connection is made to the balanced and unbalanced loads in a delta connection. So in this case, we have a 3. The figure here is a star. This is a star connection. This is a star connection. This is a star connection. So in this here, to find the total power in a 3-wattmeter method, to find the total power in a 3-wattmeter method. So to find the total power, P, the total power is equal to the power in wattmeter 1, you add the power in wattmeter 2, and then you add the power in wattmeter 3. So for example, if you had the power 1, you had power 1 to be equal to 50, watts, and then power 2 to be, let's say, 40 watts, and then power 3, let's say power 3 to be equal to 150 watts. So to get the total power in this 3-wattmeter method, to find the total power in this 3-wattmeter method, so you take the power of wattmeter 1, that is 50, plus the power of wattmeter 2, that was 40, plus the power of wattmeter 3, that was 150. So you sum the 3, that is 50 plus 40, you get 90, plus 150. So the total power will be equal to 240 watts. The total power will be 240 watts. That is how you find the total power in 3-wattmeter method. Moving on to an example. So for example, we want to show the total power in a 3-phase, 3-wire using the 2-wattmeter method, and then we find the phasor. We show the total power in a 3-phase, 3-wire system, and then in a 2-wattmeter method, then you draw the connection diagram. Then we draw the phasor diagram for the 2-wattmeter method for a balanced load. Then using the phasor diagram, we should derive a formula from which the power factor of a 3-phase system may be determined only using wattmeter readings. A connection for the 2-wattmeter method of power measurement is shown in our next figure. A connection is shown in our next figure. This is the connection we had earlier of a 2-wattmeter method. So it's for a star connection, So the total instantaneous power, the total instantaneous power will be ER multiplied by IR, then EY, Y is the yellow phase, R is the red phase, and B is the blue phase. So the total instantaneous power will be the voltage in the red coil, in the red phase, in the Y phase and the blue phase, and in the 3-phase system we have the current in the red phase, the blue phase, and the yellow phase. They will be equal to 0. They will be equal to 0 in a 3-phase system. Hence, we can see that IB, that is the current in the blue phase, IB is the current in the blue phase, IR is the current in the red phase, and the IY is the current in the yellow phase. We have just rearranged our equation. This is our equation that we have rearranged to get this one. So the power, we replace the values. We want to replace the values. We want to replace the values. We want to replace the values. So we had our IB as IR minus IY. We had our IB is equals to the minus of IR and then the minus of I1. So if we are replacing in our equation, we have our equation as P. Our equation as P is equals to ER. E is our voltage in the red phase, multiplied by IR, Then we have the voltage in the yellow phase and the current in the yellow phase, that is EY, IY. And then you add the voltage in the blue phase, Then you substitute by our equation. Where you have IB, you put negative IR, Then minus IY will be equal to what? It will be equal to the same. It will be equal to ER. We have common terms here. ER minus EB, where we have, when you open the brackets here, you have ER, and then you have, when you open the brackets from this equation, the one we have just written, you have ER minus, IR, and then you add EB, So when you open the brackets here, you have ER, IR, and then you have EB minus EB, IR, minus EB, IR, minus EB, IY, and then plus EY, IY. So when you open the brackets, this is the resultant. You put the like terms together. These are the resultant. You put like terms together, and you find that equation. So moving on to our next point. When ER is equal, ER minus EB is the potential difference. ER minus EB is the potential difference across wattmeter 1. ER minus EB is the potential difference across wattmeter 1. This one in wattmeter 1. And EY minus EB is the potential difference across wattmeter 2. So the potential difference across wattmeter 2, we have said, is EY minus EB, that is the voltages. And in wattmeter 1, we have ER minus EB. Those are the potential differences in the two wattmeters. So the total to find the total instantaneous power is the power in wattmeter 1 plus the power in wattmeter 2. That is how we use to find the total power in the two wattmeter reading. The moving systems of the wattmeters are able to follow the variations which take place at the normal frequencies, and they indicate the mean power taken over a cycle. That is how, so hence the total power is P1 plus P2 for either balanced or unbalanced loads. Moving on to our next question, it was asking about drawing a Phasor diagram. This is a Phasor diagram that we came up with. This is a Phasor diagram. From our drawing, from our figure, we came up with a Phasor diagram. So the Phasor diagram for the two-wattmeter method for a balanced rod, having a lagging current. So it's shown, this is the figure of our Phasor diagram, where VRB, that is the voltage across the red phase and the blue phase, VRB, the voltage across the red phase and the blue phase, we say is ER minus EB, that is the same as ER minus EB is the same as VR minus VB. That is now the voltage across the red phase and the blue phase. And we say that in the voltage across the yellow phase and the blue phase is Vy minus Vb or Ey minus Eb Phasorially. These ones are added and subtracted Phasorially or using the Phasor diagram. So in wattmeter 1, using the Phasor diagram, the VRB, that is the voltage across the red phase and the blue phase, multiplied by IR, that is the current in the red phase, multiplied by the cos of 30 degrees minus phi will give us P1, will give us power 1. The same happens to wattmeter 2. That was the voltage across the yellow phase and the blue phase. But in this case, now we add the cos of 30 degrees plus phi, giving us the power 2. Adding the 2 or dividing the 2, rearranging the 2 gives us this equation. When you rearrange the two equations of P1 and P2, they give us this equation. So since IR is equal to IY, since the current in the red phase is equal to the current in the yellow phase, we have, and the voltage across the blue phase and the red phase is the same as the voltage across the yellow phase and the blue phase for a balanced rod. We substitute the two where this is the same, VRB and VYB is the same, IR and IY is the same or they are equal. So we get this equation. We get that equation. So from our compound angle formula that we learned in mathematics, the compound angle formula that we learned in mathematics, we have this equation. We rearrange the two equations. Then we arrange the two equations of power 1 and the power 2. We replace it by that. When we rearrange the two powers of power 1 and power 2, power 1 and power 2, we get that. So 1 plus the tan of tan 30, when you find tan 30 in our calculators, you get 1 the square root of 3 tan 5, and the same applies to P2, we get that. So since sine over cos is equals to tan 5, since sine over cos, from mathematics, sine over cos is equals to tan, or when you use a formula of SOHCAHTOA. So sine over cos is equals to tan. Now, when you cross multiply, you find P1 to be that's how you find P1 and P2. So P1 is equals to P1 minus P1 over root 3 tan phi is the same as P2 plus P2 over root 3 tan phi. That is how you cross multiply. Cross multiplying here, when you cross multiply, here we had P1, here we had P1. We want to cross multiply and see. Here we had P1, here we had P1 over P2. So when you cross multiply, you cross multiply P2 with the numerator and P1 with the denominator. So when you cross multiply, here we have P1, here we have P2. So when you cross multiply, you have P1, you multiply with the denominator, you have P1 into the brackets, P1 into brackets, 1 minus 1 over root 3 tan of phi. That is how you find P1. That is P1. And then when you go to P2, P2 you multiply with the numerator, P2 you multiply it with the numerator, where you have 1 plus 1 over the root of 3 tan phi. So this is the resultant of P2 after substituting, after simplifying. So P1 minus P2, you rearrange this equation. So P1 minus P2 is the same as this one. So from which tan phi, the formula that we use to find the power factor, we saw earlier, tan phi is the same as the root of 3, P1 minus P2 over P1 plus P2. This is how you find the power factor. That is how you find the power factor. So phi, cos phi, and thus the power factor can be determined from this formula. That is how you find the cos factor. That is all about today, how to find the power factor. To find the power factor, you use a tan phi. To find the power factor, you use a tan phi. So to calculate the power P1, So to calculate the power P1 or in wattmeter 1 is equals to 3 multiplied by the wattmeter reading. You multiply by the wattmeter reading. That is how you find power in wattmeter 1 or in 1 wattmeter. So to find the total power in wattmeter 2, total power in wattmeter 2 is equals to the total power in wattmeter 2 is the same as P1 plus P2. That is how you find the total power in wattmeter 2. To find the total power in wattmeter 3, it's PT. That is P1 plus P2 plus P3. That is how you find power in 3 wattmeter reading. And this is how you find the power factor in a 2 wattmeter reading. That is how you find the power factor in a 2 wattmeter reading.